We have seen that in a computer system or a microprocessor based system, the microprocessor talks to the memory to get the instructions to be executed. Sometimes it also gets data from the memory or from the input output devices. Now, as far as the user is concerned, if the user wants to get some program executed, so the user has to enter the instructions that we have that the program has to in some binary format into the memory, because the memory ultimately stores only binary information. So, the program that we have, so that has to be coded into binary, and this binary program has to be loaded into memory. Now, when the microprocessor is reset, okay, so there is a set address from which it starts. In case of 8085, that address happens to be 0. So, it accesses location 0 and reads the first instruction from there, executes the first instruction, then it goes to the next instruction. So, that way it continues. So, as you can understand that any computer system starting at address 0 should have some monitor program or some operating system program. So, which will in turn transfer the control to the user program, and after the user program is over, then that control will be transferred back to the operating system. So, that is how the whole system works, but as far as the microprocessor is concerned, it reads instructions from the memory, and if the data is needed from memory, so it will read the data also from the memory, execute the instruction, and then it will place the result back onto memory or onto the output device, as the situation may be. Now, in this execution process, you can understand that there are 3 stages. The first part of it, when the microprocessor reads the instruction from memory, so that is known as the fetch operation. So, it is fetching the instruction from memory. So, the processor does not know whether it is an instruction or data or whether it is meaningful or not, but it will interpret that for the first access will give it the instruction. So, that will be that is called the fetch operation. Now, after getting the first word from the memory, so it may so happen that this processor will understand that okay, this is the processor will understand that it needs some more part of the instruction or maybe more data from the memory. So, for that purpose it has to decode the instruction. So, after decoding, the processor understands what exactly has to be done, whether it needs data from memory or not, whether it needs some data from some input output port or not, IO device, etc. And then after getting those data, it will execute it, and in the execution process may be some operation followed by storage of data. So, this entire thing comes as the execution. So, you can say that after the way the processor works is, first it performs the fetch operation, then after fetching the instruction, the processor enters into a phase which is known as the decode phase. So, from fetch it comes to the decode phase, and after decoding the instruction it goes into execution of the instruction. So, this is the execute phase. So, these are the 3 phases that we have in instruction execution: fetch, decode and execute. So, after the execute is over, so processor is done with the current instruction. So, it should get the next instruction from memory. So, what it does? It now goes back to the previous next fetch operation to get the instruction from the to get the next instruction and execute it. So, this way this fetch, decode, execute, it forms a cycle. So, if you look into any processor, so it will have this fetch, decode, execute cycles. Okay. So, that is they are actually, in some sense you can say that they are pipeline. So, fetch followed by decode followed by execute. So, in 8085, so there is no overlapping of these stages, but if you look into later processors, you will find that there is an overlapping of these stages. When the first instruction is fetched, so no other instruction can be fetched at that time. After that, the first instruction goes to the decode stage, and at that time the next instruction may be fetched. Then when the instruction the first instruction goes into the decode stage, the previously fetched instruction So, when the first instruction in the decode stage, the next instruction can be in the fetch stage, and when this first instruction goes to the execute phase, when it goes to the execute phase, the next instruction goes to the decode phase. So, this goes to the decode phase, then this instruction goes to the second instruction goes to the execute phase, and in the meantime the third instruction. So, when the second instruction was in the decode stage, so third instruction was being fetched, then the third instruction goes into the decode stage, then it goes to the execute stage. So, that way there is an overlapping between this fetch, decode, execute. So, if you look into say this particular cycle, then the first instruction is executing, second instruction is in decode stage, and third instruction is in the fetch stage. So, this is also known as fetch, decode, execute pipelining. It is common in many of the processors. Now, so this sequence of this fetch, decode and execute, it continues till all instructions are done. So, how do you know all instructions are done? Like any processor, it will have an instruction, so which tells the processor to halt. So, there is an instruction like halt. So, when this halt instruction is executed, then the processor halts its execution. So, all the signals are in you can say inactive stage, and so to take the processor out of this halt stage, a special mechanism known as interrupt has to be used, and when this interrupt is received, then the processor comes back to wake up mode, and it will again start executing from some defined address. Okay. So, this is the sequence of operation that happens in the execution of instructions. Next, we will see how this program can be written, like the binary program that we have talked about. So, how this can be developed. So, we will introduce that terminology called machine language. So, we are familiar with many programming languages like say C, C++, Java, etc., but these languages, they are for to some extent human understanding. So, as a human being, so if you read a C program, you understand the meaning of that, but a machine or a processor does not understand a program in that language. See, it only understands the binary zeros and ones. Okay. So, when you interpret the program that you have written in a high level language into a language which is understandable by the machine, so this is called a machine language. So, in case of a microprocessor, the number of bits that form the word of a microprocessor is fixed for that particular processor. Word means in one access how many bits it gets, or when it is doing some operation, some arithmetic logic operation. So, what is the minimum number of bits on which it is operating. In case of 8085, so we will say that it is 8-bit processor, because all the operations are 8-bit operations. So, if I say that my word size is say 8-bit, that means when you get the first instruction, when the processor is in fetch stage, it gets the first instruction, and then that 8-bit pattern, it will depict what is the instruction. So, naturally, so this with 8-bit I can have at most 2 power 8, that is 256 combinations. So, these bits will define a maximum number of combinations that are possible for the machine instructions. However, in most microprocessors, all these not all these combinations are used. 256 is a very large number, but as far as these simple processors like 8085 is concerned. However, for complex processors, that number may not be that significant. However, for complex processors, the word size is also large. So, it is 16 bits. So, that way your instructions the number of possible combinations is also very high. So, when the processor fetches a word from the memory, so its type will determine the meaning of the meaning of that word. Okay. So, so out of this all combinations that are possible, all combinations are not used, and it is up to the designer of the processor to choose certain patterns and assign them some specific meaning. Each of these patterns will form an instruction for the processor. So, suppose I have got 256 patterns. Now, as a designer of the processor, I see that my processor will be executing 100 different instructions. So, I will be satisfied with 100 different codes. So, rest of the codes are do not care for me, because the processor will simply ignore those codes. So, these patterns they will so each of these 100 words, so they are actually one instruction for the microprocessor. So, this complete set of patterns it will make the machine language of the microprocessor. So, this is called the machine language. So, the language which is understood by the machine. Let us look into 8085 machine language. So, as we have said that 8085 is an 8-bit microprocessor. So, 8-bit microprocessor, as I have said, that it is the external data bus size is 8-bit, and internally when it is doing the operations. So, all the operations are on 8-bit data. So, with 8-bit, so we can have 2 to the power 8, that is 256 different combinations are possible. Okay. So, when this processor this is 8085 and this is your memory, then as I said that in the at the very beginning it does a fetch operation and gets 1 byte from the 1 word, that is equal to 8-bit from the memory. Now, this with this 8-bit I can have 256 different patterns possible, but in case of 8085 out of these 256 patterns only 246 patterns are used. So, remaining 10 patterns are not used by the processor. So, it uses a total of 246 different bit patterns to form the instruction set, and these 246 patterns they represent 74 instructions. So, 74 types of instructions. We will see that within the same instruction there may be variants. So, that is why for 74 instructions we will need 246 different bit patterns. So, it is very difficult now as a user of the microprocessor system. So, if I am asked to write the program in this binary number system, binary bit pattern, then it is very cumbersome. Okay. So, normally we can use some hexadecimal instead of binary. For example, if the bit pattern that I want to have, that I have to enter is like this 00111100, which for in case of 8085 this corresponds to the instruction that increment the number in the register called accumulator. So, this 8085 has got a special register accumulator, and this particular bit pattern, okay, to the processor it will mean that it asks for incrementing the accumulator register. So, we will see in detail after some time. So, instead of entering the data as 00111100, so we can break it into 2 hexadecimal digits, and this is 3 and this is C. So, 3C. So, we can, if we have got a hexadecimal keypad, so we can enter these 2 digits very very easily, 3C. Okay. So, this way it can be done. Now, this hexadecimal type of entry, so that is also not very much comfortable for the users, because then so if you look into a program that is written in this hexadecimal codes, then naturally it looks very cryptic. So, as a reader of the program we do not understand the meaning until and unless for each instruction we look into the corresponding meaning from the manual. Okay. So, we need to bring some amount of readability of the program even in this machine language version. Okay. So, that gives rise to another level of language which is known as the assembly language. So, entering instructions in hexadecimal is easier than entering in binary combination. However, it is still difficult to understand what a program written in hexadecimal does, because as I said that I need to interpret each and every hexadecimal number that I have entered. So, what has been done is that different companies they have define a symbolic code for the instruction. So, as I said that previously we have seen this instruction that increment the number in the register called accumulator. So, instead of writing this big statement, it may be simply increment may be written as say INR. So, it may be simply INR and this accumulator is A. So, this is INR A. So, by this text we understand that it is asking for incrementing the register A. So, here you see, so this is so it is easier to, so instead of hexadecimal number, So, we can have some symbolic code for the instruction, and these codes are called mnemonics. For example, that INR A, the INR part is known as the mnemonic, and A is the operand on which that mnemonic works. So, as a designer of the processor, so we can think about different mnemonics that are possible, that we are going to use, and using those mnemonics. So, we can as a user of the system, we will know that those mnemonics and write programs using those mnemonic. The mnemonic for each instruction is usually a group of letters that suggest the operation to be performed. So, this is as I said that it's a INR. So, it is a combination of I, N and R. Almost all the processors will have some mnemonic called MOV, MOV. So, these are quite common. So, we will see as we proceed into the assembly language of 8085. So, as I said that this 0011 1100. So, this is 3C in hexadecimal. So, this hexadecimal code is called the op code or the operation code. So, this actually tells which operation has to be done. So, that is why it is called op code. So, this bit pattern or this hexadecimal code. So, this is called op code, and the mnemonic is INR A, where INR is the actual mnemonic part and A is the operand. Okay. So, A is the shorthand for accumulator. So, instead of INR A, so it may be some other register also. So, that is the incrementing that particular register. So, INR part is the mnemonic and this A is the operand. Take another example. Suppose we have a bit pattern 10000000. So, this is a 80 in hexadecimal, and if you look into the manual of 8085, you will find that this particular code corresponds to the mnemonic add B. Okay. So, where add is actually the mnemonic and B is the operand. So, this whole thing is an instruction in the assembly language. So, what it does, this is an instruction that tells the 8085 microprocessor that the user wants to add the register B to the accumulator and keep the result in the accumulator only. So, this is what the user wants is something like this. The accumulator A should get the content of register B added to it. So, A gets A plus B. Okay. So, this is there. So, this way the assembly language programs, they actually help in understanding the meaning of the machine language program to the users, not to the processor. So, processor is happy with the machine language code in some binary format, but for human understanding, so this is in assembly language. So, it is important to remember that a machine language and its associated assembly language are completely machine dependent. So, if you learn the machine language, if you learn the assembly language of one processor, it is not going to be same as the assembly language of another processor. So, because this is done by the processor designers, and they do it at their own effort, you can say, or at their own wish. Okay. So, it is very much unlikely that the two processors will have exactly same assembly language. There will definitely be some difference as because the assembly language is very close to the actual hardware. So, since the actual hardware between two processors are varying, so this assembly language is also going to vary. So, that is why, so normally we learn programming in a high level language and then use some tool by which the program is translated onto say machine language, or it can also be translated to assembly language. So, if you look into say any C compiler, normally these C compilers, they do have an option by which it can tell it to keep the assembly version of the translated program. So, it actually from your high level language program, it generates the assembly language program, and from the assembly language program it generates the machine code. So, you can tell the processor, you can tell the compiler to keep the assembly language code available as a separate file. So, if we are expert in the assembly language of that processor, then we can look into that code and possibly try to optimize that code further. So, if you look into say Motorola's 8-bit processor 6800. So, this is so 8085 is from Intel and this 6800 is from Motorola. So, this 8085's assembly language is machine language is very different from that of 6800, and so is the assembly language. So, they are different. A program written for 8085 cannot be executed on 6800, or vice versa. So, that is true. So, it is so the target has to be specified, like if you are installing any compiler, you must be knowing that it asks for the target processor for which the code has to be generated. So, this is because of this reason that the machine language or two different processors are totally different. So, something targeted to one processor will not work with the other processor. Now, as I said that from the assembly language program is for user understanding. So, machine or the processor does not understand it. So, what we have to do is we need to translate this assembly language program into machine language program. So, how do we do it? First we can do an hand assembly. So, we look into the manual of the processor, and then for every instruction that we have in the assembly language. So, we just see what is the corresponding instruction corresponding machine language code. So, programmer will translate each assembly language instruction into its equivalent hexadecimal code, and then this hexadecimal code values will be entered by some keypad, and ultimately the when it is entered, that software which is getting the data from the keyboard will finally store the corresponding binary pattern into the memory. So, this is the hand assembly process. So, for simple processors like 8085, it is possible that we do an hand assembly and get the get the assembly language program translated into machine language. The other option is that we have an assembler. So, assembler is a tool that can translate assembly language program into machine language program. So, this assembler can be used that will translate the assembly language code into machine language. Now, as I was telling, so if I have got some high level language program, say I have got a C program, .C program. So, it passes through a compiler. Now, this compiler, it generates some assembly language program. So, let us say the extension is .asm, and then this assembly language program, it passes through an assembler. This passes through an assembler and it generates the machine code. So, this is the machine code. So, now if you can write directly in the assembly language, so you do not need this part. So, you can start straightway at this point, and then you can you can run the assembler and get the machine code. So, normally when we are doing this translation, this C compiler, so it integrates the assembler with it. So, we see this whole thing as the compilation process. We see this whole thing as a compilation process, that is why we do not see the assembler code. However, you can tell the compiler to keep the assembly file .asm file for your viewing and doing some further optimizations. So, that is done by the automated tool called assembler. Next, next we will be looking into this 8085 microprocessor architecture. So, these assemblers are definitely it is targeted to different processors. So, if you are looking for 8085, we will target it to 8085. Otherwise, you can tell that okay, it is for other processors, so it will do it accordingly. Now, in case of 8085, as I said that it is an 8-bit general purpose microprocessor. So, general purpose microprocessor means it is not doing some special operation. For example, if you are doing some signal processing tasks, so there are digital signal processors that are used for that. Then for graphics processing, we have got some special graphics processors. So, like that, but 8085 as a processor, so it is a general purpose processor. So, it can do the basic arithmetic operation, logic operations like that. So, it is not specific for a particular application. It is capable of addressing 64 kilobyte of memory. So, this is so total memory space that it can address is 64 kilobyte. So, with 8085 system, so you can connect memory up to 64K, and if you want to connect, it is not that you cannot connect beyond this, but for that purpose, so you have to take some extra hardware for the connection, but up to 64K So, it can be directly interfaced with 8085. So, since 8085 comes as an IC chip, so it has the chip has got 40 pins in it. The power supply requirement is plus 5 volt. So, the clock frequency it can operate is with 3 megahertz, and it is upward compatible. So, upward compatible means that if you have got some older versions of some processors, then this is so that you can just take up that chip and put this chip into the system. So, that is there. So, that is upward compatibility is maintained. So, as far as the 8085 pin diagram is concerned, so here it is like this. So, it is a 40 pin chip as I have said. So, pin numbers are 1 to 40. Out of that, so pin numbers 1 and 2, so they are called x1 and x2. So, this is a frequency generator is connected to those pins. So, normally what we do is that we connect a crystal between this 1 and 2, okay, and the crystal frequency will determine the frequency at which this 8085 will work. So, that the frequency generator is connected to this 1 and 2. Then another important line is VCC. So, this is the power supply plus 5 volt, and there is a ground line. So which will be giving us the ground. So, this VSS. So, this is the ground line. So, other important pins if you want to see, then it has got this address bus. So, this is A8 to A15. So, this is the higher this is a higher order address bus, and these pins AD0 to 7. So, AD0 to 7. So, that will constitute the lower order address bus. So, as I said that 8085 has a memory space that it can address is 64K. So, for 64K we need 16 bit bus, okay. So, 16 bit, because 2 power 16 is 64K. So, 16 bit is obtained like this. So, here I have got bits A15 to A8, and here I have got pins A7 to A0, okay. So, A7 to A7 is this one, pin number 19, and A0 is this one, pin 12. And we have got say 8, it is an 8 bit processor. So, whenever it accesses data from outside world, so it is in terms of 8 bits. So, that 8 bit data bus is this D0 to D7. So, this is D0, so this is D7. So, this address 0 and data 0, so these two pins are same. Similarly, address 1 and data 1, so these two pins are same. So, this is called, so we will see that to reduce the number of pin count, so it has been done like this. Otherwise, what would have happened is that the 16 bit address line, so that is 16 pin, and 8 bit data line, so that is 8 pins. So, 16 plus 8, 24 pins would have already been done just to create this address and data lines. So, we will not have much other pins left for other operations, okay. So, to just so the designers they have done some multiplexing of this address and data buses, so that the number of pins required is less. Now, there are some additional pins that we will see slowly as we proceed through this course, but some important pins like this is the read bar signal. So, read bar signal, so this is activated when the processor wants to read something from the memory. Similarly, write bar, so this is activated when the processor wants to write something onto the memory. Then there is S0, S1, so these pins, so that gives me the status line. So, there are actually 3 pins, the IOM bar, S1 and S0. So, they tells what the processor is doing at present. So, if you just want to know probe the processor and see what is it doing. So, this IOM bar, S0 and S1. So, this will tell you this will give you some indication about what the processor is doing now. Apart from that, so there are some interrupt lines INTR and these line trap, RST, this 5.5, 6.5, 7.5. So, they are actually some facility by which you can interrupt the normal operation of the processor and tell it to do something special. Okay. So, this is that this is for that interrupt. So, we have got this another important pin that we have is through this SID and SOD. So, this is serial input data and serial output data. So, if you want to transmit some bits serially from this 8085, so you can do it via these SID SOD pins. Okay. So, as we proceed further, we will be looking into more and more details of these individual pins. like say we will be actually viewing these pins in terms of functional groups, that is the functions that they are doing, and we will try to group them together.